So, hi everyone, welcome to the Industrial Problem Seminar. It is a great pleasure to introduce Dr. Pratik Jain. He's a well-known researcher in machine learning who leads the Machine Learning Foundations and Optimization team at Google AI, Bangalore, India. His research interests are in machine learning, non-convex optimization, high-dimensional statistics, and optimization algorithms. He's also interested in applications of machine learning to privacy, computer vision, text mining, and natural language processing. Earlier, he was a senior principal research scientist at Microsoft Research India, and he completed his PhD at the University of Texas at Austin under Professor Inderjit Dillon. And he's going to talk about pitfalls of deep learning.
Hi, Gilad. Thanks so much for the introduction and thanks for having me here in this webinar. And thanks all for attending this talk. Please feel free to interrupt and ask questions in between. I think Gilad will probably, I think you'll need to type them and Gilad will convey those questions. All right. So today I'll talk about some of our recent work in the direction of understanding deep learning and what its pitfalls are and maybe how we can try to address them. This talk tends to raise many more questions than really answering them. So that's why I'm really looking forward to the discussion here. Before starting with the actual talk, let me quickly give a very brief overview of Google Research India, which itself is relatively young lab. We will complete, I think, 3 years in next week, and the lab is set up in Bangalore. So I would love to invite all of you to visit in case you are coming to India or to Bangalore. The main goal of the lab is to deliver impact on scientific front as well as on the societal front, as well as contribute very meaningfully to Google products and our customers. And despite it being a very young lab, there have been a fair bit of success stories coming out of the lab in terms of impactful projects, scientific progress, collaborations with various NGOs to deliver AI, which is helping society in meaningful manner, as well as fairly strong contributions to Google products. And our lab covers most of the prominent AI-related areas like computer vision, NLP, core machine learning, cognitive sciences, HCI, etc. Right. And in particular, I lead what we call machine learning and optimization team. And our team has 5 research scientists, 3 research engineers. And along with that, we have a very exciting group of what we call pre-doc researchers, who are basically people who finish their undergrad and they spend a couple of years with us working on cutting edge research problems. And typically, then they go for their PhD at really top institutes. And we also tend to have a fairly steady diet of research interns and student researchers, etc. So in case if you are interested in some of the work that we are doing, please feel free to reach out to me and we can try to see if we can somehow host you. The overall vision of the team is to come up with ML models that are easy to deploy. That is, there is a lot of work going on in the community to come up with new ML models, new training methods, new data sampling methods, etc., to train models which perform very well on some given benchmarks. Our goal is to sort of say that once you have developed such models, how do you ensure that those models are deployable in real world? And many times the real challenge starts there. And there are various aspects to it. For example, even if there is a slight bit of distribution shift in the data, that tends to break down the models really significantly. So one big line of work that I will discuss in today's talk is to understand why these models are so brittle and what we can do to fix them. Then another big aspect when you want to deploy a model for inference is to ensure that your model does not reveal sensitive information about some of the individual data points that you might have used for training. So we're focusing a fair bit on learning models that are differentially private, that is, the preserve privacy of each individual data point in the model, or from which the model is trained. And finally, many times, ML currently seems to be about scaling. That is, you want to have bigger and bigger and bigger models, but then when you want to infer with them, the cost might be too high, especially if you want to deploy those models in real-time settings, especially on, say, mobile devices. So a big part of our effort is to see if we can come up with ML models that are much more efficient to infer with and can be deployed on tiny devices as small as a low-end smartphone in global south, which might not even have a good GPU to infer with. Right. So with this sort of picture of our team and the main focus areas for us out of the way, let's now dive deep into uh, the the key question that we want to understand in this talk, which is that why do deep learning models fail drastically in a variety of settings. So for example, on benchmarks, we know that deep learning models are working really really beautifully, but then when you see a little bit of distribution shift, or you see a little bit of small, very minor adversarial attack to the deep learning models, that is by changing the data points a little bit, they seem to completely fall off the map and give really poor performance. And furthermore, many times we observe that these deep learning models tend to exacerbate bias in the training data also quite a bit. So we want to understand why that is happening. And so in this talk, we'll try to understand why these neural networks are so brittle and how can we identify these brittle spots, right? So we have made some progress towards answering these questions, making them a little bit more formal, and basically giving at least some kind of, I feel like, a target that, oh, this is the main challenge or main problem that you want to solve. But do I have a solution for that? Frankly speaking, no. And that's why it's a very sort of, exciting direction. So let's start with a very simple thought experiment. How do, like when we look at these images of say swan and bear, how do we distinguish between them, right? So as a human being, I think we would be looking at a bunch of features to distinguish between animals in these two images. For example, we'll be looking at the colors, the background, the shape, organs, etc. And then we'll say that, this image contains a swan, whereas this image contains a bear, right? Now the question is, does neural networks also learn in this holistic manner? That is, as neural network also looking at all these features that are potentially available in the image, right? So here, the answer seems to be somewhat in the negative for a big for a variety of sort of tasks that people have studied. So one very sort of interesting experiment was conducted in this very nice work by Garrios and co-authors, where they showed that your state of the art vision models tend to focus mostly on the texture in the image rather than the actual shape. So for example, if you just show this image on the leftmost, even though it does not see the shape of the object or the animal, it is able to still sort of guess that, oh, this is an Indian elephant. It is able, like the model is powerful enough, so it is able to identify this cat also properly. But now if you transfer this texture of elephant onto the cat, then the model gets completely confused. It is just saying that it's an Indian elephant, and cat is not there even in the top three predictions, right? So this clearly shows that neural network is not looking at all the features holistically. It seems to be preferring texture much more over shape, right? Similarly, there was this very nice work by DeGrave. We showed that when you train your model for, let's say, identifying certain infection in your chest X-ray, then their model, rather than learning the actual actual patches where the infection might be, it seems to be focusing significantly on some of the markings that were there in the hospital. And that means that if you give some another X-ray where those markings are not there, the model completely fails. It gives, so on training data it gives really high accuracy, but on the validation data where such markings are not there, it gives completely garbage answer, right? So the question is that, so it does seem like that, okay, neural network is not maybe looking at all the features. It seems to be looking at some very specific type of features. So A, why are neural networks learning only some features? And B, can we understand what type of features do neural networks learn? And is it what type of features it is completely ignoring? right? And that's mainly the contribution of this work. That is, we sort of uh, hypothesize that neural network is indeed learning very small number of features, and furthermore it seems to have some kind of extreme bias towards very simple features. That is, it is learning, trying to just sort of focus on the simplest of the features and ignores completely, like, other set of features. So let me make this hypothesis and, like, some of these vague terms little bit more clear. Let me use one example to make it more concrete, right? So let's consider two-dimensional data points. We have feature phi1 on x-axis here, and then feature phi2 on y-axis here. And the points are color-coded. So these are all, let's say, points belonging to class negative, and these are all like red points belong to class positive, let's say class red, right? So here you can see that feature phi1 is actually on its own able to separate out these class red points from class blue points, right? But if you look at it, the margin for this feature is very, very small. On the other hand, there is slightly more complicated feature, right? Like basically a, say, a 5 piecewise linear classifier, which has really good margin and is able to separate out these points very well, right? So now one question is that, let's say if you train your favorite neural network, let's say maybe some MLP neural, like multi-layer perceptron network with, I don't know, say 5 layers, hundreds of neurons in each this thing, and I give you a lot of samples. Like I'm ready to give you, let's say, 1,000,000 samples, right? And you use your favorite optimizer, let's say Adam or Adagrad or whatever you want to use. The question is, which boundary will you learn? Like, will you learn this linear boundary, or will you learn this slightly more complicated boundary, right? So it turns out that in practice, like, when we started the project, I presumed that the neural network will learn this slightly more complicated boundary because that boundary seems to be sort of optimizing margin. And at least, like, when we think about margin in the standard support vector machine world, uh, it does correspond to the distance from the hyperplane. So the notion of simplicity, that is the, let's say, the norm of the classifier that you're learning, and the distance to the boundary, they sort of match very well. So in that case, like, based on that intuition, I at least thought that, this network will be learning this complex boundary. But it turns out that no matter what we did, like, how many layers in the neural network we put, how many neurons we put in the neural network, what optimizer we used, what initialization we used, the network almost always learned a boundary very close to the linear classifier. And it almost never learned this more sort of complicated but better margin boundary, right? And then, like, as we were trying to understand what's going on here, we realized that there is some kind of like rigorous reason for this. Like, this is not just happening by fluke or by due to some bug in our experiment. There is some kind of rigorous reason for why this is happening. But before going to that rigorous reason, uh, like, we call extreme simplicity of neural networks to be precisely this bias towards learning extremely simple classifier or extremely simple features. That is, features which can be captured by a very small network in some sense over slightly more complicated but larger margin features. So neural network is somehow completely trading off the margin as in like the traditional notion of margin, where, like, let's say points are far away from the boundary, for this very, very simple classifier or simple features. So that's what we call extreme simplicity bias of neural network, right? Uh, and as I said, like, at least in some cases, we can come up with a rigorous proof for why this is happening. So one such setting for which we are able to showcase is that, let's say, if you consider a one hidden layer neural network, where K represents the number of neurons in the network. For simplicity, we fix the second layer and we are just learning the input layer or the first layer, right? So here, suppose we have data of this type, we extend this data to d dimensions by adding some random features in all the remaining d minus 2 dimensions. We initialize the weights using standard initialization scheme. The number of samples is also fairly large, let's say more than order d square, and it is an over parameter setting. So the number of neurons that we are taking, like, that is the k, is pretty large. Like, it can go as much as d square, right? Uh, So even in this setting, what we show is that at least standard SGD, if you train your neural network with the standard SGD, the linear feature, like this feature 5, 1, that gets a weight of say about 1 by root k, right? Where k is the number of neurons. And the non-linear feature, that is the feature which captures like the phi2, and which captures basically this kind of boundary, that feature has weight of at most 1 by root dk, right? So this says that the linear feature is basically of root d bigger or more powerful than the non-linear feature in terms of like the features that neural network learns. So that sort of says that yeah, like it is basically ignoring the feature phi2 and it is just using feature phi1 to do its classification. So any questions so far? Yeah.
There is one question by Priya. What was the
Yeah.
training data type, text and image for this experiment?
So this is very, very simple two-dimensional data point, right? I have just feature phi1 and feature phi2 for each data point that I give. So like this is pretty much the data that I give. Only thing is that we extend this data to d dimension, where the remaining d minus 2 dimensions are all, let's say, Gaussian, random Gaussians that have no correlation with the actual label.
Okay. Another question by Arun Kumar. Is not that what NTKs as well?
No, so we are not in NTK regime in some sense, right? Like we are taking these WJs and we are training them, and we are training them. We are okay training them as much as you want. So we are not stopping in some kind of lazy regime. So it's not actually NTK kind of setting.
Okay. Thank you. Any other questions? Thank you.
Okay. Yeah. So why is this happening, right? So when we look at the proof, it's the proof is fairly simple. Like basically, what happens is that when you write down your gradients, right? The gradient with respect to the feature phi1, that turns out to be much, much larger than the gradient with respect to the other features. And the reason for that is that, these other features have some kind of, like feature phi1 has very direct correlation with the actual label. So that's why every neuron basically reinforces that direction. But for this feature phi2, there is a little bit of anti-correlation going on with the actual label in certain places, right? Because let's say this is when you look at just this direction, for certain time you have one label, then the label changes, then again the label changes, again label changes. So because of this, some of the gradients get cancelled out of some of the neurons, because of which what happens is initially the gradient is significantly more aligned with feature phi1 compared to feature phi2, right? So because of that, neural network basically uses that initial direction of gradient and moves in that direction. And after taking a few steps, it would have already killed the loss so much that the gradient that remains, like the residual that remains, is so tiny that it is not able to move the nonlinear features much at all. So because of this, basically, we are not able to learn anything other than linear boundary, like mostly, right? So that's sort of a high level bit of why, I'm hoping that I convinced you that neural networks do exhibit this, what we call this extreme simplicity bias, which means that it is learning extremely simple features and is ignoring more informative, larger margin, more robust features in favor of these very extremely simple features. And there is a fundamental reason for this. This is not just happening by fluke. So next we I'm when I'm calling this simple, I'm talking about these things like piecewise linear and all, which is somewhat unclear or somewhat vague. So we try to make this definition a little bit more formal. So we came up with slightly more formal definition, which was that we said that okay, when you look at your neural network, let's consider again just one hidden layer, multi-layer perceptron, although this definition can be extended to multiple layer perceptrons as well as to convolution networks, etc. So here what we do is we consider this matrix W, which consists of all the weights in the hidden layer, right? So basically consider this matrix. So So we define simplicity bias in this type of network as basically when the rank of this W matrix is small, right? That is, if this W matrix is aligning all the neurons towards one of the direction only, then that says that you are not using all the features in the data. You are just using one type of feature in the data, right? And in particular, we define this little bit more formal metric that we call effective rank of W, which is essentially exponential of entropy of the singular values of matrix W, right? So here now we are able to provide, like, once we consider this kind of definition, we can actually provide a even stronger result than this result that we provided here. So here in this result, we had one linear feature, one what I would call non-linear feature, right? That is, there is some bit of non-linear boundary here, and then there were a bunch of random features. And then here, just for SGD, we showed that SGD converges to a linear boundary, right? So it raises multiple questions that, oh, um, uh, what if I had more such nonlinear features? Would neural network ignore all those nonlinear features in favor of this one linear feature? A. B, the question would be that what if rather than SGD, I use some other method like say ADAM, ADAGRAD, or some other like margin optimization method? Would I converge to more sort of complicated boundaries rather than the linear boundary? So to address those questions, we consider a sort of stronger setting where we said that okay, again, let's say we have d-dimensional data point. The first direction is completely correlated with the actual data set, but like the correlation, there is the coefficient gamma which sort of controls how much we are correlated, and then the remaining features are very similar to this type of this second feature. That is, uh, it basically what it says is that for when you have, let's say, the positive label, the feature can either be say +1 or -1. But if it is the negative label, then it is always 0. So in some sense, it is a 3-slab kind of situation. That is, I have a positive slab in this direction, then a negative slab, or like basically y is equal to minus slab, and then I again have a y is equal to plus slab, right? So here note that there is only one linearly separable direction, and then there are d-1 features which are all informative, but they require basically a 3 piecewise linear classifier to do that separation. So there are d-1 non-linear features in some sense, right? So here what we were able to showcase was that as long as this correlation is greater than some constant, and that constant is completely independent of the dimensionality of the data, the max margin classifier. So it doesn't matter whether you're using SGD or you're using ADAM or ADAGRAD. If your classifier is converging towards a particular definition of max margin, which was defined by this very nice paper by Chizat and Bach, then the max margin classifier will always have rank 1. And in fact, that rank 1 classifier, that is like all the features are aligned with this first feature, like this 0th feature, which is essentially the linear classifier or linear feature. So this result says that A, we have extreme simplicity bias because the rank of the matrix is 1. And furthermore, which feature are we learning? We are just learning the linear feature. We are not looking at any other feature, no matter how much data you are giving there, right? So note that, like, this is now completely independent of D. So basically, even if you take D to be exponentially large in whatever things you want, it is still completely ignoring all that, and it is going to just look at that linear direction. Any questions about this? Great. So, so like, I mean, this is all like, this might seem like, okay, this is all well and good, but maybe this is a bit too cooked up, right? That is, we cooked up this particular type of data sets to demonstrate that there is an extreme simplicity bias of neural network, but maybe my realistic neural network trained on realistic data will not have this issue at all. So let's try to see if that's actually the case. So to understand this, we constructed some semi-real data sets. So one type of data set that we constructed is what we call MNIST-CIFAR data set. So here what we do is we take, let's say, 2 types of digits from MNIST data set, say digits 0 and 1. And we take 2 types of classes or classes from CIFAR dataset, say cats and dogs, right? And then in training data, what I do is I always pair a 0 from MNIST image or MNIST block with a cat from the CFAR data set, right? And basically I concatenate these two images, and that gives me the final, like the super image on which I train my model. And I call let's say this as class 0, right? Similarly, I take 1. I always in the training data concatenate with the image of dog, make that as a super image, and I will call that as class 1, or let's say class positive, right? And then I train my favorite neural network. Say I train my Google Net model on top of it. So for this model, right? In general, like, so network will learn certain logics, right? So basically network processes this images and then finally produces some logit values, which essentially shows how much confident the network is in certain prediction, right? So here, let's say we are looking at class 0. So it is producing for that class 0, it produces logits which are pretty large in value, right? Now, what we do is we take this, like in the validation data, we take the CFAR part, right, and randomize it. That is, I always have, let's say, 0, and I have, let's say, sometimes I have a cat, sometimes I have a dog, right? But what we observe is that it doesn't matter whether I have a cat or dog there, my logit values do not change at all. So that indicates that my network does not care whatsoever what happens to the CFAR part. It is just looking at whether I have my 0 from the MNIST block, and based on that, it decides whether it is positive class or negative class. And furthermore, it also decides its confidence in it. That is, it gives the logit values, whatever it is, right? On the other hand, if I keep my cat image as it is in the validation data, but I randomize my zeros, like the MNIST part, that is, I replace some of the zeros with a 1, then I very clearly see that the logits shift significantly, and they shift to the negative or to the positive, basically, right? So that indicates that the network is not looking at CFAR part at all. It is just looking at the MNIST part, right? And why that might be happening? Well, that might be happening because of the extreme simplicity bias of the network. That is, we can construct much simpler networks to do 0 versus 1, right? So for example, even a linear classifier tends to do pretty well on 0 versus 1. But for cat versus dog, the network that you need is slightly more complicated. Again, the network with which we are training has the power to do cat versus dog. It is able to get 99% or so on cat versus dog. But because we appended it with 0 versus 1, the network completely ignores the cat versus dog thing and completely hones on to the 0 versus 1 problem. Right? That is, its features are completely aligned with 0 versus 1 task rather than cat versus dog. Any questions about this? About this setting and this result? Okay. So so you might say that, oh no, but Pratik, maybe you did some cheating. Maybe Google and it has some particular bias for simple features or for MNIST block versus CFAR block. So we tried actually, like, a bunch of other standard models, like, MobileNet, ResNet, DenseNet. DenseNet is one of the bigger models in general. And like, we didn't try the VIT models, which are a little bit more recent, but I'm pretty sure the performance remains pretty much the same. But for these models, what we observe is exactly the same story repeating. That is, as soon as you randomize the MNIST part, the accuracy of prediction in some sense drops from 100% all the way to 50%. But if you randomize the CFAR part, the accuracy remains pretty much the same. That is, the model does not depend at all on the CFAR part. It's mostly just depending on the MNIST part, right? Now you can say that, oh, but what if I change my activation function? Maybe rather than ReLU, I use leaky ReLU, p-ReLU, 10 hyperbolic. Doesn't really matter. Like, again, similar sort of story is there. We can change our initialization scheme also. Again, doesn't matter. Like, pretty much the same story remains, right? So this is just to say that, like, no matter how you are changing things, and even if you're changing the data set a little bit, it doesn't matter. Like, same kind of issues occur. In fact, like, this There are we had a little bit more interesting experiments conducted as part of this project. So for example, we observed that what we did was we trained a bunch of binary MNIST classifiers. So we did 0 versus 1, 1 versus 2, 2 versus 3, like all these 10 choose 2 binary classifiers we trained. And then we looked for small enough models which classifiers had the highest accuracy. So for example, generally say 0 versus 1 had very high accuracy, whereas I think 3 versus 8 had very small accuracy, like low accuracy relatively, like 4-5% lower accuracy. So what we did was we concatenated 0 with 3 and 1 with 8, right? And again, when we trained our model, we observed pretty much the same phenomena. That is, network was almost exclusively focusing on 0 versus 1, and it was completely ignoring 3 versus 8. Like it would again, like if I randomize my 3 part in the validation data, it will have no impact on the logits. Logits would be as if it's just looking at the 0 part or the 1 part, and it ignores 3 versus 8 part completely. Any questions? All right. So you might have this criticism that, but Pratik, this is still some data set that you constructed, maybe on real data set. So maybe on my, let's say, ImageNet data set or so, this issue is not there. So it turns out that that's also not the case. So for example,
so Pratik,
yeah,
one moment.
Yeah.
I see a question here.
Sure.
Data. What if you can? What if you can put a cat or dog on the top and 0, 1 on the bottom of each image? How about systematically merging the two pictures?
Yeah, so we did try a bunch of those experiments. So you can put like 0 versus you can put cat on top, 0 on the bottom. You can also do this other experiment where you take cat and superimpose 0 there. So you take the cat image and you just put 0 somewhere, right? And you can do other way around also. You can take the 0 image and you can put small cats, and not just one cat. You can put multiple cats there. Again, no matter how you do it, at least based on our experiments, it will almost always go towards 0 versus 1 thing, and it will almost completely ignore cat versus dog thing. And I think, yeah, the reason, at least according to us, is basically the simplicity bias. That is, 0 versus 1 can be captured by much simpler network. It just looks at that, ignores the cat versus dog feature. Okay. Any other questions? All right. So as I was saying that you might have one more criticism that, oh, but this is a data set that you constructed. Do I face this problem in real world in some sense? So what we show is that even on the real world, actually the data, like the model tends to have extreme simplicity bias. So here what we did was we took a subset of ImageNet. And what we did was we took a pre-trained network. So we took I think ResNet 50 pre-trained network, right, on ImageNet. And then to solve this sub problem of ImageNet, we, on top of that embedding from the pre-trained network, we applied a one hidden layer neural network, right? So exactly the same kind of setting that we had in the theoretical result. And then we trained our model, right? And what we observed is that initially the network was giving attention to the entire pre-trained embedding. That is, it was learning using all the features in the pre-trained embedding. But as we went along and our accuracies increased, the effective rank of the network kept on decreasing, right? That is, network started to hone on to some simple features and completely focus on those simple features only, and it completely ignores all the other features. So as you keep on training, it keeps on sort of honing onto some small number of features, right? We observed a very similar phenomenon, almost replicated curve on this problem that's called water birds, land birds. So basically here you have certain birds which are observed against water and against land. And there again, the same thing happens that initially, and we again did the same, like we used a pre-trained ImageNet model on top of which we had one hidden layer neural network trained to do the classification of water bird, land bird. And we observed that initially the network was using all the features, but then as you keep on training to increase your accuracy, it is aligning towards only some of the features, and it completely ignores all the other features. Okay. All right. So you might say that, okay, sure, my neural network is learning these simple features. In literature, in fact, generally it is touted as a good thing because that might be the reason which explains why neural network, despite having so much of capacity, is not overfitting and is generalizing so well, right? So that's true. That's great. But there are consequences of this, at least of extreme simplicity bias. I agree that there should be some simplicity bias in the network and the architecture in our training method, but there seems to be some kind of extreme simplicity bias, right? Where slightly more complicated network or slightly more complicated boundary can capture than that like the actual robust margin, but the network is not learning it, right? So that's why we are calling it extreme. So why is this extreme simplicity bias bad? So well, the reason is that this is our hypothesis that according to us, this is the main reason why the network has such poor adversarial robustness, out of distribution robustness, and sometimes when you are in very low data regime, actually it can lead to poor in-domain performance also. So let's understand this slightly better, right? So if you consider this two-dimensional cartoonish example, here it's very clear, right, that if the network is learning the linear boundary instead of this complicated boundary, then you take this one feature phi1 and you perturb it slightly, your accuracy will drop significantly. You perturb just this area little bit, and you can easily have 10% drop in accuracy, right? And this also explains some of this phenomena that people have observed, which is that of universal adversarial brittleness, right? That is, irrespective of the network, people have come up with some small, simple adversarial attack, which will always hurt any network that you train on. And again, our hypothesis is that because the network is learning some very simple feature, if you go and attack that simple feature, you'll always win. Like then it doesn't matter which network you're training. All the networks will be brittle against that, and that's what is at least in happening in this cartoonish example. Then other issue that obviously this leads to is out of distribution performance. That is, instead of this training data distribution, again, if my feature phi1 shifts little bit, my distribution shifts little bit, my performance can drop very drastically, right? And the reason for this in-domain performance issue is it's a little bit more complicated, but basically imagine that if I don't have these many data points and I'm in much higher dimension, so then rather than learning a larger margin solution, which tends to be more robust and so which means that even though I don't see a lot of points, I would try to be away from most of the points. Instead of that, what I will do is I will try to just sneak by my existing points, and that would again lead to significant drop in accuracy, right? So I hope I convince you that yeah, simplicity bias can be one significant reason for really poor performance of neural networks in light of say adversarial attacks or out of distribution attacks. So now the question is, how do we fix it, right? So there are a few approaches that come to mind, and they are somewhat successful, I would say, but nothing I would say is completely successful. Nothing that is able to solve problems like say this MNIST-CIFAR kind of problem. Like so far, almost none of the existing results is able to do it. So one type of approach is that of ensemble. That is, what you do is you say that, okay, I will train my multiple networks, and I hope that at least some of the network will end up learning more complicated feature. So one thing that I can guarantee is that just random ensembling is not helping at all, because the inductive bias is so strong for the network to learn the linear boundary that it almost always just learns the linear boundary, never learns any of the other features, no matter how many random runs you have. So random ensemble is not helping. One recent technique that we have come up with, which do tend to help, is that you train your network, let it learn the linear boundary. That is, the W matrix that we have is going to be rank 1 only. But then what we do is we take that rank 1, right? And in the next, so we now train the next model. In the next model, what we do is we always project the W matrix in in sort of orthogonal direction to the rank 1 direction that we had already learned. So basically, you learn the linear feature or simple feature, and then the next network you try to learn, you keep on projecting out that direction so that you are sort of focusing on other features now. again, this technique is definitely working better, at least for this simple, simple like cartoonish examples. But still, for this MNIST-CIFAR kind of cases and all, these techniques are still not giving us very good results. Right. Now, another approach is to maybe try adversarial training, right? That is, adversarial training is known to sort of promote robustness. So maybe by promoting robustness, it will make sure that the network is not learning the simple boundary and it is learning more complicated boundary. So at least in the experiments that we tried fair bit of variations, like standard adversarial training with L infinity type of perturbation, L2 kind of perturbation, various different type of training mechanisms. And at least in our this thing experiments, none of that really helped, especially on this MNIST-CIFAR kind of problem. Neither adversarial training helped, neither nor ensembling helped, nor like more intelligent ensembling helped. So this MNIST-CIFAR type of problem seems to be really open, and I feel like that captures the crux of the problem in many ways. So somehow figuring out solution to this problem would be quite interesting, right? Now, at the same time, what I would definitely want to sort of say is that I don't believe that just by changing the optimization algorithm, we can solve this problem, because our standard optimization methods tend to have convergence towards like standard gradient flow based methods or gradient flow type of methods tend to converge to max margin kind of solution in the, and that max margin is not the distance to the boundary, but it is defined in a particular way. So for example, in this Chizat and Bach paper. So because of that, because our regularization itself sort of promotes that kind of margin, and we can here, for example, earlier we showed that that kind of max margin solution would give you low rank solution. That is, it is favoring only one of the feature. So because of that, I feel like actually there is a problem with our regularization itself. That is, until unless we come up with some different type of regularization or a problem, uh, it doesn't seem like just changing the optimization method would help. So either the optimization method has some very different type of inductive bias, or we change the regularization and then use our standard methods like SGD or ADAM or RMS prop and all. Any questions? All right. So in the remaining about 12 minutes, I will try to cover one more sort of interesting direction. So as we were trying to sort of fix the simplicity bias, one thought that we had was that if, let's say, I can identify um, what features are contributing to a certain classification, then I can maybe blank those features out. Like as I mentioned earlier, like try to zero it out or try to sort of project it out, and then just work with the remaining features and try to learn more complicated thing there, right? So for example, in this MNIST-CIFAR, the hope is that if I can identify that, these pixels are the ones who are responsible for me calling this image as a class 0 image, then I can blank it out, and then I will start learning more about the CAT features. Right, so I will want to blank out 0 and 1, and then hopefully my network will start learning more and more about CAT versus dogs. Right, so that requires us to figure out some kind of feature attribution, right? That is, for a given instance, we want to figure out what features or in the input data were the reason for my networking predicting certain class, let's say, right? So feature attribution is a very sort of popular problem in explainable AI type of domain, right? And the goal is, given an image, you want to come up with some kind of attribution map that basically that basically highlights what part of the image was the actual response was actually responsible for your final prediction. So for the rest of the talk, let's just mostly assume that we are dealing with image kind of data points, although you can sort of generalize most of these observations to any domain or any type of data points. So sorry, what happened? So there are a lot of gradient-based feature attribution methods, where the idea is that we take the prediction that is coming out of the network and we differentiate that prediction with respect to our input, right? And the intuition is that if by changing certain part of our input, the prediction changes a lot, then that says that that part is the one which is responsible for that prediction, right? And that's why, like, we will be able to estimate what part of the input is really responsible for certain, like, prediction of the network. Right? And there are a lot of these feature like gradient based methods. So, like, if you use just basic gradient, then this is maybe how your predictions look. But then there's a method called smooth grad, guided backprop, guided grad cam. So there are a bunch of these methods based on it. Mm, One sort of question now comes up is that, okay, which attribution method should I use? It's very hard to come up with any kind of uh, objective metric to select a gradient based attribution method, because you don't really have any ground truth, right? Like, how do you assign a ground truth to this thing, that okay, which feature is the most important one that my network should look at? Like, it, even for humans, it's hard to sort of claim that, oh, this is the feature that should be responsible for certain prediction, right? That's for general images. So many times people look at these images that come out of these feature attribution methods, and based on that, they say that, okay, oh, based on this, oh, maybe the gradient based method is not as good as, say, smooth grad, right? But then people have shown that that is also not a great idea, because even if you just use edge detector kind of thing, that will also start highlighting like the main object. And because of that, even model agnostic things would look good in terms of how these images look. So just by looking at the image, you might not want to select a certain attribution method, right? So so the question that we sort of started to ask was that, okay, a like, do this discriminative, like, this feature attribution method based on gradients, do they work or not? And if not, then why not, right? So to sort of understand this, we need two things, right? So one is we need, like, to sort of tease out the actual underlying assumption that these methods are making when they are saying that, oh, based on gradient we are attributing certain importance to certain input data or input coordinates. So there's some underlying assumption there that we want to tease out. And the second thing is that because of the lack of ground truth or information, uh, like, it's hard to sort of figure out whether a method is working well or not. That is, whether it is satisfying the underlying assumption or not. So for this, what we've done is, A, we have sort of brought out the underlying assumption very clearly, and B, we use sort of a multi-pronged approach using real and design data sets to understand whether these gradient attribution based methods really work or not, right? So as I mentioned, like, the underlying assumption in some sense that you can tease out of these gradient based feature attribution methods is that if there's an input coordinate that has a large gradient, then that would be more relevant. Like, it's hard to sort of say, like, in terms of absolute terms. So we would say that, okay, that is more relevant for your model prediction than a coordinate which has much smaller gradient, right? So that's the underlying assumption. Now the question is, does the neural network which are, like, trained in practice, do they satisfy this assumption, right? So as I mentioned, like, we use bunch of real and design data sets to sort of understand this assumption. So our, like, main result is the following, that we came up with like, a Diffroor framework to verify whether a certain assumption is satisfied or not. And what we do is that actually we provide very strong evidence that standard models that you train typically do not satisfy this assumption. That is, if you train a standard model, you compute the gradient, then the largest, like, the input coordinates where the gradient value is the largest, might not correspond to the most important feature in some sense. But what we do observe is that adversely trained models, that is, if you apply this adversarial perturbation during your model training, then this assumption might be satisfied. Now, there would be one question, which is that, okay, why do standard models do not satisfy this assumption, and why do adversarial trained models do satisfy this assumption? So we have a particular hypothesis that we call feature leakage, that we attribute to, like, this issue in gradient-based attribution methods. And furthermore, we have some sort of, theoretical analysis that shows that there is indeed, like, some kind of feature leakage in fairly simple data sets. So let me quickly, like, I have maybe about 5 minutes. So let me very quickly describe the Diffroor framework. So Diffroor framework, what it does is, let's say if you have some kind of instance, right? And you have some feature attribution method, right? So it's a gradient based feature attribution method. So based on the attribution, we will take the top K features according to our method. And we will just keep those top K items unmasked, and everything else is masked. And similarly, we will take the bottom K items and keep them unmasked and mask everything else, right? So intuitively, because top K is keeping the most important things unmasked and bottom K is keeping the most, like, least relevant things unmasked. So if you, take this kind of thing, train your model again with this top K unmasked and bottom K unmasked data, then the accuracy that you get, right, on the top K unmasked versus bottom K unmasked, that should be pretty different. Like that should be very large. That is, if you take your prediction using just top K unmasked minus prediction using bottom K unmasked, that's what we are calling Diffroor accuracy. The Diffroor accuracy in general should be very high if this assumption is correct. That is, your feature attribution method based on the gradient is indeed highlighting the important features, right? Do you agree with this part? Okay. So this is how we trained. We have presumed that, oh, our model will give this Diffroor accuracy to be very high, especially for, like, when the fraction of pixels that we are unmasking is very small. But what we observed was something completely opposite that was happening. That is, let's say if we take, say, image one subset of ImageNet that we call ImageNet 10, basically taking, like, 10 classes of ImageNet and training our ResNet 18 model on it. Based on that, then we computed, based on the ResNet 18 model, we computed the gradient of the input images. We did the masking thing or unmasking of the top K thing, bottom K thing, computed the Diffroor metric. And what we observed was that for very small, like, K values, actually the Diffroor metric was very negative for our standard training, right? So that was quite surprising, that it basically says that this assumption that we had, that, oh, if certain feature has large gradient, then that feature would be important. That does not seem to be holding true at all. In fact, the bottommost feature seems to have more information in some sense than the topmost features according to the gradient values or gradient norms, right? But what's interesting is that if you train your model with some kind of adversarial perturbation, so let's say if I train my network with L infinity perturbation of, say, epsilon of 4 by 255, these are images normalized between 0 to 255, like every pixel is between 0 to 255. So in that case, what we do observe is that the Diffroor metric is quite positive. Naturally, as you keep on increasing fraction of unmasked pixels, the Diffroor metric will keep on coming down, because the difference between the top K unmasked and bottom K unmasked becomes very small, right? Uh, so any question about this result? All right. So, like, this again is something which we observe very consistently. So whether you use ResNet architectures or MLP architectures, whether you use ImageNet or Fashion MNIST or CIFAR, we observe very similarish trends, right? So one question is that, why is this happening, right? So to understand this, we had one, like, very specific type of data set on which we trained our model. So what we did was we took, let's say, 0 versus 1 problem in MNIST, and we formed these super images where we concatenate the MNIST image with some kind of null pattern. And sometimes that null pattern can be at the top, sometimes that null pattern can be at the bottom, right? So this is class 0, where the null pattern can be at the top or the bottom, and this is class 1, where the null pattern can be at the top and bottom, but you always have this digit 1. Right. So here when we train our model and then like a standard resonant model, and then we look at the image gradient, what we observe is that not only the gradient is highlighting the actual feature, but it is also highlighting the feature at the top, right? So that clearly sort of indicates that gradient or the feature from this other image in the training data got leaked onto this training point, right? Or this test validation point. So basically, that's what we are calling feature leakage. That is, gradient from the entire training set is sort of leaking into one another, and that leads to this confusion in the attribution method. What's interesting is that when you train your model using, say, adversarial perturbation, say L2 adversarial perturbation or arithmetic perturbation, then the network is indeed zoning onto the actual feature, and it is completely ignoring the other features. Right? So that's what we are calling feature leakage. Again, there is a very crisp reason for why this feature leakage happens. For some very simple, like data distribution, which does match, like this type of data distribution that we have here. We showcase this feature leakage rigorously for standard models. That is models that you train using standard SGD or ADAM. And we also sort of have partial result for adversary trained model. That is, for adversary trained model, we do observe that this kind of feature leakage does not happen. I don't have time to go in details of this, but please feel free to look at our paper if you want to look at more of these details. Let me now just conclude, which is that I hope I convinced you this talk that neural networks can exhibit this extreme simplicity bias. And this extreme simplicity bias is not good. It can lead to brittleness of neural networks in practice. And we are trying to figure out a bunch of methods to break this simplicity bias. Most of these techniques have not been so successful. One technique that we thought would be useful would be based on feature attribution, but there the issue is that because of feature leakage, feature attribution methods themselves are not working well. They are working well when you have adversary trained models, but now the issue is that if you have adversary trained models, then the accuracy already is so low to begin with that even if we identify the attribution very well, that might not mean that we will solve the simplicity bias problem very well. So because of this, there is like sort of this open problem of how you can solve this extreme simplicity bias well. So that's all I have. Mentioned, there are a bunch of questions here. Main is how to tackle simplicity bias in neural networks in general. But I feel like, even if we can solve the problem, it's a very specific type of settings and specific type of data distributions that are also quite useful. Okay. Any questions?
Yeah, thank you very much. This was a really interesting talk. And I'll let people type the question. In the meantime, I can ask you various questions. So one thing that I'm not sure about, it seems to me that there are some simpler data set where it's still an advantage to have, simplicity bias. Like, if I think of ECG signals, so they have very simple features, like, radiologists have, the Q waves and very, very simple features, and neural networks actually can get much better than what even cardiologists do. And still with simple features, we have kind of high correlation with what cardiologists have. So here we see actually an advantage to have
certainly. So I'm not saying that simplicity bias is bad. Like, as I said, like the simplicity bias in some sense is boon, because of which our networks are able to generalize, right? Like if the network is learning arbitrary boundaries, you will not even generalize, you will just overfit. But the problem that we are highlighting is that many times network is going for just the simplest features and is ignoring even slightly more complicated features. Now it's very hard to sort of, sort of, make it more precise. That is, what do I mean by slightly more complicated? As I said, like, one definition is to say that, okay, if you can use very small network to learn certain feature, then that's like a slightly more complicated feature. Another is the rank thing, right? That is when you are like at least towards the rank end of your network, if the matrices that you're getting are like sort of more full rankish, then that would help you avoid this issue where you are just looking at one or two very simple features at the cost of larger margin. So I agree that you want to look at simple features, but the question is that if I have 5 or 7 fairly simplish features, do I look at everything holistically and then combine them and have like a little bit more powerful and robust prediction, or I want to just phone on to one feature and that's it, like just focus on that and ignore everything else.
Okay. Yeah, and I agree about this. And actually, in this, data of ECG signals, it's easier to do feature, attribution and kind of see what's going on there. So I think it might be interesting to do it. Another thing that I'm kind of curious because it seems to me that a lot of the adversarially robust methods also try to kind of carefully find the boundary that you have. So, you only talked about adversarial training, but there might be, other methods. They have, I have to check, but I was thinking about another thing. I just have to check the reference, but did you check other adversarially robust methods?
We did, again, like, it's hard to claim that you try, like, we tried everything, but we did try most of the main popular methods. So like, L2, L infinity, like, this gradient descent ascent kind of methods. Then we did try this another thing that people call like, where, like, you have distributional robustness kind of method. So I forgot what they are called.
I'll follow up. I'll check one
Yeah.
reference that I have in mind. I'll follow up with you later.
Yeah, but we did try like at least few of them and didn't seem to matter much. Yeah.
Interesting. And did you also try, see the effect of this on generation tasks and kind of getting mode collapse in generation?
Sorry, can you come again?
So did you kind of try to explore the effect of simplicity bias on generation?
No, we did not. We haven't. Yeah, that we haven't tried yet. I don't remember if any paper explored this. I do remember that there were a few papers which showed that this simplicity bias exists also in self-supervised learning. So here, like, we had supervised learning tasks, but even if you want to do self-supervised learning kind of things, there also people demonstrated that if you have like that, there also people demonstrate that there can be extreme simplicity bias. Generation, we didn't explore it, but yeah, that's a great sort of direction to look at.
Let's see, any other questions? I think some students need to leave for classes. So yeah, thank you very much. It was really a great talk. I really enjoyed it, and I'll follow up with you afterwards.
Yeah, thanks so much for having me here, and yeah, definitely looking forward to follow-up emails. Yeah.
Okay.